Welcome to Brain Vision.
Consider a spherical bead with a radius of 4 millimeters. The bead has in its center a cylindrical hole with a radius of 1 millimeter. If the bead has a constant density of 2 grams per cubic millimeter, we want to set up a triple integral in cylindrical coordinates that will give us the mass of the bead, and we want to evaluate this integral. So first, let's draw a schematic. We'll start by drawing an x, y, z coordinate system. And draw a sphere in the middle. Within our sphere, we have a hole, a cylindrical hole, with a radius of 1 millimeter. So this length here is 1 millimeter, whereas this length here is 4 millimeters. So we want to find the mass of the bead. First, we need to recall how the mass density is related to the mass and the volume of our bead. So rho, the mass density, will be equal to dm over dv, which means that the mass will be equal to the volume integral of rho dv. And in our problem specifically, rho is a constant, so we can remove it from the integral, so the mass will be equal to rho times our volume integral. So we essentially want to find the volume of our solid here, which is the sphere minus the volume of the cylinder. And we want to do so. We want to evaluate this integral using cylindrical coordinates. So first, let's recall what are cylindrical coordinates. Cylindrical coordinates use coordinates z, r, theta, where z here is the same in Cartesian coordinates, r here is different than in spherical coordinates, because here r corresponds to a radius within the xy plane. So let's say any radius from here to here, as opposed to a radius starting from the origin. And theta is defined as the azimuthal angle. So the angle that the radius makes with respect to the x-axis. For example, if we were to consider a radius here in the xy plane, this angle here will be theta. So we have then cylindrical coordinates. The radius is equal to the square root of x squared plus y squared. As opposed to in spherical coordinates, the radius is equal to the square root of x squared plus y squared plus z squared. So now we're almost ready to integrate. We just need to recall what is the volume element in cylindrical coordinates. In Cartesian coordinates, we know the volume element is equal to dx times dy times dz. But in cylindrical coordinates, dv is actually equal to r, dr, d theta, dz. Whereas r here is the Jacobian. So now to find the mass, we can evaluate the triple integral of r, dr, d theta, dz. We need to establish now the appropriate lower and upper limits of our integral. The easiest will be theta, because we know theta will scope the entire circumference of the bead. So theta will range between 0 and 2 pi. And r, the radius in cylindrical coordinates, will vary between 1 to the outer boundary of our sphere. Why 1 is because below 1 we have a hole. So we essentially want to integrate between our cylinder, the wall of the cylinder, to the wall of the sphere. So this is r. So our lower boundary would be the constant r is equal to 1, but our upper boundary will be the radius of our sphere, which we know is equal to the square root of x squared plus y squared plus z squared, where x squared plus y squared is equal to r, which means that we can rearrange this equation, r squared. We can rearrange this equation and we'll see that r, the radius in cylindrical coordinates, is equal to the square root of r squared minus z squared, where r squared in this case will be the constant 4. So we will have that r will be bounded by the square root of 4 squared, the radius of our sphere, minus z squared. And z will be bounded by the entire height of our sphere, which will vary between plus 4 to minus 4. So now we've just determined all of our lower and upper limits. Let's write those in. So r will range between 1 and the square root of 4 squared minus z squared. Theta will range between 0 and 2 pi. And z will range between minus 4 and 4. So now we've just set up our triple integral. Let's evaluate. The integral on theta will be easy to evaluate because our integrand does not depend on theta. This will give us 2 pi times rho times the integral over z from minus 4 to 4 where we'll be integrating r squared over 2. This is the integral of r dr for r ranging between 1 and the square root of 4 squared minus z squared. So now we're just left with an integral over z. But before that, let's first evaluate r between 1 and its upper limit. So evaluating r squared over 2 within its lower and upper boundary will give us 4 squared minus z squared minus 1. Which will we write to? Whoops. In the integrand, we will find 15 minus z squared dz. Now we note that this is an even function over a symmetric integral, or a symmetric lower and upper boundary. So this will be equal to 2 times pi rho times the integral from 0 to 4 of 15 minus z squared dz, which will give us 2 pi times rho times 15z minus z to the power 3 over 3, where z will range between 0 and 4. Evaluating this, we will obtain 2 pi times rho times 15 times 4 minus 4 to the power 3 over 3. And simplifying this, we will obtain a pi rho times 29 over 3. And rho in our case is equal to the constant 2 grams per cubic millimeter, which means that our mass will be equal to 16 pi times 29 over 3 grams.